Hi, everyone. In this video, I'm going to go through the study guide for the honors stoichiometry quiz, the Unit 8 quiz. There's 3 questions on a worksheet. I'll link it in the description. And it's only 3 questions, but there's quite a lot of parts to each one. So let's start. 623 grams of heptane gas burns in the presence of 1.79 kilograms of oxygen. So type of reaction, it's pretty straightforward. It's going to be combustion, because we have a hydrocarbon fuel burning in air. What mass of carbon dioxide will form? All right, so here's where we're diving into the real problem. So the first thing we're going to do is balance our equation. So C7H16, I tell you that's a gas, plus O2 gas yields CO2 gas plus H2O gas. All right, let's balance. So H16, so I'm thinking 8. Is an 8 going to be okay? Yeah, that's fine, because that's an even number of O's. C7, so I'm going to put a 7 there. And it should be this plus half of that for 11. And let's just confirm 7 O2s is 14, 8 O's is 8, 14 and 8 is 22, half of that is 11. Good. All right, so I always like to rewrite my coefficients underneath just to kind of make them pop. All right, what mass of carbon dioxide will form? So I told you the mass of heptane, but I also gave you the mass of oxygen. That makes this a limiting reactant problem, okay? Anytime you're given both the masses of both reactants, or the moles even of both reactants, you can't just pick your favorite one. You can't just pick the one that's going to be the easier mole ratio. You have to identify the LR and use that to solve for your answer. So we need to turn both of these into moles. All right, 623 grams. That's heptane times 1 mole over, so C7 is going to be 12.01 times 7 plus 1.01 times 16 is going to be 16.16. 100.23. That's the molar mass. 623 divided by that gives me 6.23 moles. All right, so I like to put that right underneath here, 6.23. That's how many moles of that I have. For oxygen, I have 1.79 kilograms. Yes, you do have to turn that into grams because molar masses are in grams. So that's going to be 1,790 grams of O2 times 1 mole over the molar mass of oxygen gas, which is not 16. It's 32 because it's O2. So 32.00 grams. 1790 over 32 is 55.9. That's moles of oxygen. 55.9 moles. Okay, so we have to identify the LR. So there's several ways of doing this. The more formulaic way is moles divided by coefficient. Moles divided by coefficient. Smaller numbers, your LR. I actually prefer to just kind of look at the numbers and work it out logically. So notice it's a 1 to 11 mole ratio. So if I start with 6.23, I'm going to need 11 times more moles over here to do that. Now, just by looking at this number, I can tell I don't have enough of this, right? Because even if I needed 10 times more, I would need 62.3. I need well more than that. So, I mean, I could literally do the math here. 6.23 times 11 means I would need 68 moles of oxygen for this to react. Clearly, I don't have enough oxygen, which means oxygen is my LR, which means heptane is my ER. Okay, doesn't matter how you identify the LR, just make sure you do identify the LR. And that's the one we have to use to solve for X, which is our moles of CO2 and eventually our mass of CO2. Again, you can't just pick your favorite. If we could, I would definitely pick the heptane because a 1 to 7 ratio is easy. 11 to 7 is tricky. All right, so next, let's solve for X, which is moles of CO2, and then we'll turn that into grams. So I have an 11 to 7 ratio, definitely a little tricky here. There's a few ways of working that out. You can use the dimensional analysis method where you just take 55.7 moles of O2, multiply it by 7 moles of CO2 per 11 moles of O2. Some people just do multiply by this, divide by that. You can also set it up where you cross multiply, where you say 11 over 55.9 equals 7 over x. So you would end up doing 11x equals 7 times 55.9 and getting your answer that way. Several ways of solving for x. I think what I'll do is I will take my 55.9 and I will multiply it by 7 moles of CO2 per 11 moles of O2. So I multiplied times 7 over 11, and I got 35.6 moles of CO2. I multiply that by the molar mass of CO2, which is 44.01. You do the same types of problems enough, you'll memorize certain numbers. So times 44.01 gives me 1570 grams of CO2. And that is this one, 1570 grams. Okay, part 3, what mass of excess reactant will remain unreacted? Okay, so here's my ER. I started with 6.23. I know that not all of that's going to react. How much will? Well, we can figure that out. We're looking to find how much is left over. So here's how we do this. You don't start with the ER, you start with the LR, because all of this is going to react. So if this much reacts here, how much of this is going to react? Well, it's an 11-to-1 ratio. So if we divide this by 11, we'll see how much of this will actually react. 55.9 divided by 11 gives me 5.08. So 5.08 will react. So I'm going to say minus 5.08 to see how much we have left over. 6.23 minus 5.08 is 1.15 moles remain unreacted. We're looking for mass. So I'm going to multiply that by this molar mass, which we already found down here. 1.15 times 100.23 gives us 115 grams unreacted. So 115 grams. All right, last part. If 1.24 kilograms of CO2 are collected, what's the percent yield? So obviously, if we're collecting CO2, we're looking for percent yield of CO2. Well, percent yield is experimental yield over theoretical yield times 100. Experimental means how much you collected, and according to this problem, we collected 1.24 kilograms. Theoretical is how much was supposed to form. Now, we already calculated that. 1570 grams. Now the units obviously have to match, so we'll call this 1.57 kilograms. You can make them both grams, get the same answer. So 1.24 over 1.57, I'm going to guess that's going to be like 80%. Let's see. Pretty darn close. 3 sig figs, 78.98. I'm actually going to call it 79.0. Okay, so I'll write that in here, 79.0%. Okay. Yeah, and obviously the calculator said 0.7898. You're going to multiply that by 100. All right, so that's it for this problem. Let's move on to the next one. Okay. Zinc chloride and potassium phosphate. So we have 2 solutions being mixed. So type of reaction is going to be double replacement reaction. We're going to complete a BCA table. Now, I said in the notes above, this is something that I definitely focus on. Your teacher might not focus on this specific strategy. So if you've never heard BCA, don't worry about this. It obviously won't be on your quiz. But a BCA table is basically just, it's nothing new. It's just a way of organizing a problem that I feel kind of makes it easier to follow, especially if the problem has a lot of stuff you're being asked. Okay. So to start with the BCA table, we start with a balanced equation. So we have ZnCl2 aqueous. Potassium phosphate is going to be K3PO4 aqueous. The zinc and the phosphate are going to bond, Zn3 parentheses PO42. That one's going to be solid. I checked my sheet earlier. Potassium chloride, KCl, that's going to be aqueous. And we balance that with a 3, a 2, a 1, and a 6. And I like to, again, rewrite those, just kind of make them pop. All right, here's how we do a BCA table. B, C, A. Before, change, after. How many moles of each of these terms do we have before the reaction takes place? Well, for the zinc chloride and the potassium phosphate, we're going to find out. All right, 12.7 grams of ZnCl2. I'm just going to work this out kind of quickly here. So zinc chloride, zinc is 65.39, one of those, plus 2 times 35.45, 136.29 is the molar mass. So 12.7 over that gives me 0.0932 moles. 0.0923 moles. Now in the BCA table, I'm not going to write the units in because the units are always moles. For the next one, potassium phosphate, and I had 3 Ks, so 39.10 times 3. I need 1 P, 30.97, right? Yep. And I need 4 O's, which will be 64, 212.27. So I go 11.1 over that, gives me 0.0523. All right, and that's how many moles I have here. Oops. 0.0523. Okay, let's finish out the B's. How many of these 2 products do I have before the reaction takes place? 0 and 0. All right, C is change, which is how much of these reactants are going to be depleted and how much of these products are going to be created. So we need to now identify the LR. Okay, so you can either do moles divided by coefficient, smaller numbers, the LR. What I like to do is start with my smaller one and just tell myself this story here, where I'm gonna say if I have 0.0523 moles, I'm gonna need 1.5 times more of this one. So let's see if I have 1.5 times more. Well, 1.5 times more of this is 0.0785. Do I have 0.0785? Yes. In fact, I have excess, making this my ER and this my LR. Okay, the LR gets completely depleted, so minus 0.0523, leaving us with nothing. How much of the excess is going to react? Not all of it, and not this same amount. It's going to be a 2 to 3 ratio here, so 1.5 times more. In fact, I already just did that. So 0.0523 times 1.5, that's your 3/2 ratio. That's going to be minus 0.0785 moles, leaving us with 0.0138 moles remaining. All right, let's fill in the right side. So my zinc phosphate, I have a 2 to 1 mole ratio here or a 3 to 1 mole ratio here. Either one should get you the same answer. Just make sure you don't use this one. If you're going to use the 3 to 1, don't use this because that's not all reacting. You could use this though. All right, I'm going to start here, 0.0523 divided by 2 because it's a 2 to 1. That gets me 0.0262 moles. Now, are those being created or depleted? The answer is created, formed. So that gives us 0.0262 moles. And here I have a 1 to 6 mole ratio, or a 2 to 3 mole ratio, or a 3 to 6 mole ratio. Any of those three should get you the same answer. Let's do this. Since I already have this in my calculator, I'm just going to say times 6 gives us 0.157 moles, and that's being created, giving us 0.157 moles. That is our BCA table. A very nice way of organizing what's going on in this reaction. Keep in mind, every number you see there is moles. All right, number 3, how many grams of excess reactant remain unreacted? Well, we already worked out the moles, so now we just do a quick little molar mass conversion. So zinc chloride, oh, I wish I still had that. Well, let's do that again. Actually, I could probably reverse engineer that. If I go 12.7 divided by 0.0932, will that give me? Yeah, I think that would. 136.26. Let me just double check. Yeah. Okay, so molar mass was 136.27 or so. I'm going to multiply that by the 0.0138 moles, giving me 1.88 grams remaining. 1.88 grams. So 1.88 grams. All right, if this group performs this reaction and reports a 91.3% yield, how many grams of it must they have collected? All right, I think I'm gonna clear up some space here. Let me clone this page. Just give myself a little more room. I think I'm gonna do it again for my sketch. Okay, switch this back to tablet mode. All right, so let me erase some of this just to make room. All right, so percent yield is experimental over theoretical. Now, if I get a 91.3% yield, that's like saying 0.913 equals experimental over theoretical. Now, we're looking for the precipitate. That's a solid product, so that's my zinc phosphate. I know my moles here. Let's turn that into grams. Now, technically, you could find the experimental yield in moles and then turn that to grams either way. But let's turn this into grams. All right, so I need 3 zincs, 65.39 times 3. I need 2 Ps. And I need 8 Os. That's going to be 128, yeah. 386.11. That's the molar mass of this. When I multiply that by this, that gives me 10.1 grams. So that's how much is supposed to form. That's the theoretical yield. So let's erase the T. Oh, no, rewrite it. Erase the T and put 10.1 grams. So now we're just solving for E, the experimental. So if you walked into math class and saw this, how would you solve for E? Well, right now we got to get this out of here. So let's multiply both sides by 10.1. That cancels here. So essentially 0.913 times 10.1 grams gives us 9.24 grams. 9.24 grams. And that makes sense, right? Because you should have gotten just around 10. You ended up getting like 9.24. So yeah, that definitely makes sense. All right, and lastly, we need a sketch. So for the sketch, definitely need to clear up some space here. Let me erase most of my BCA table. I want to leave my reaction. This is another one of those things that I definitely focus on with my sections of honors. If your teacher had less of a focus on this, I wouldn't expect this to be on your quiz. You know, we all follow the same curriculum, but we emphasize different parts of it slightly. All right, so for sketches, I do beaker number 1 plus beaker number 2 yields beaker number 3. I put some water in my beakers because these are aqueous-based reactions. Here I have zinc chloride aqueous, meaning zinc ions and chloride ions, with water molecules pointing toward the zinc and away from the chloride. Here I have potassium ions and phosphate ions, with waters pointing towards the positive ion and away from the negative ion. In my final beaker, I have my zinc phosphate on the bottom, ZN3 parentheses PO42, settles on the bottom like that. Make sure you don't split that up. You write it as a solid on the bottom. I have zinc chloride aqueous, meaning I have not zinc, potassium chloride. So K plus and Cl minus ions randomly floating around. Now, there's one last thing we need to add. When it's a limiting reactant problem, that means we also have an excess reactant. When I poured these two beakers together, some of my excess reactant is going to remain floating around. So I need to make sure I have zinc and chloride ions present in my final beaker. Now, you're always already going to have one of those. In this case, I have chloride. So I need to add the third ion, which is zinc. Again, why zinc? Because zinc is part of the excess reactant that's missing from my final beaker. So put a zinc in there, add some waters, and we're good. Notice we don't have all four ions up here. The one missing is phosphate. And that makes sense, right? Because what would happen if I sprinkled in some phosphate ions? Well, they would react with the zinc to form more solid. So notice that we were limited in the amount of potassium phosphate. And in fact, we can clarify that a little better. We technically weren't limited by our potassium phosphate. We were limited by our phosphate because we actually have remaining potassium that didn't do anything. We call those spectator ions. All right. Good on this one. Let's do the last problem. 38.2 gram piece of strontium chlorate completely breaks down over time. Ah, yes, a nice throwback at the end too. So identify the type of reaction. Well, if something's breaking down over time, that's going to be a decomp reaction, decomposition. What is the mass? What mass of the solid product is formed? Okay, so here's the real stoic. All right, so we have strontium chlorate. That's going to be SR parentheses ClO3 close parentheses 2. Because this is an ionic compound, we're going to assume that it's solid. Breaks down over time. So this is one of those exceptions, or not exceptions, but one of these types of reactions you had to memorize as an honors chem student. And that's that metal chlorates decompose into metal chlorides plus oxygen gas. So the metal chloride for strontium would be strontium chloride, SrCl2, plus oxygen gas. Now, SrCl2, that's an ionic compound, so it's going to be solid. Now you might say, hold on a sec, according to my activity series, strontium chloride is aqueous. Yeah, but that's when it's that's when water's available for it to dissolve in, right? But in this reaction, it's not like you're adding water and mixing it. There's no water here. This is one solid decomposing into another solid and giving off some gas. All right, so that's our reaction. All right, 38.2 gram piece of strontium chloride. So we got to turn 38. Oh, forgot to balance. Let's see. Let's see. Why do I feel like I made a mistake when I prepped this before? Yeah, whoops, I made a mistake when I was prepping this. Okay, because I'm noticing my strontiums are good. My chlorines are good. The only thing that's not good is the oxygens. I have 6 here, so I need to put a 3 here. All right, let's hope this doesn't mess my numbers up. Okay, so we have a 1:1:3 mole ratio. So actually, this should be a pretty straightforward problem. Let's turn our grams into moles. So 38.2 grams of strontium chlorate. So 38.2 grams. All right, so we have 1 strontium. It's at 87 or 67. 87.62. That's 1 strontium plus 2 chlorines. 35.45. Plus 6 oxygens is going to be 96, right? 6 oxygens, yeah. 254.52. So 38.2 divided by that is going to give me 0.150 moles of my starting reactants. So 0.150 moles. Okay, notice a nice easy mole ratio. That's going to give me 0.150 moles of strontium chloride. Let's turn that into grams. So strontium is 87.62. We're going to add 2 chlorines to that. And that gives me 158.52. We multiply that to get our answer, which is 23.8. 23.8 grams. Okay. All right. Let's solve the throwback. I'm going to go ahead and clone this page just to save the equation, give myself some room. Okay. Erase some of this work here. Okay. So in this part of the problem, we are assuming that you put this piece inside a 1 liter container, suck out all the air, and let the reaction occur. So as this reaction occurs, the solid is just going to sit there, and the gas is going to be released into the container. Now, actually, I'm thinking of a very small detail. Technically, the volume of the container would no longer be 1 liter. It would be 1 liter minus the volume of your solid. Now, that's micromanaging on a super crazy scale. So actually, if you want to find the density of strontium chloride, figure out what volumetric, what volume it would occupy and pull that away from the 1 liter. Actually, that'd be an accurate way of doing this. But we're going to assume it's a 1 liter container minus the solid in there. The idea is, we are going to generate a certain amount of gas, and that gas will occupy a 1 liter volume at 23 degrees Celsius, and using Pivnert, we can solve for the pressure. All right, let's find how much gas is going to form. Well, if it's 0.150 moles of this, it's going to be 0.450 moles of this. And we multiply that by 32.00, that's the molar mass of O2, 0.450 times 32 gives us 14.4. Oh, wait, you know what? We're going to be plugging moles into Pivnert, not grams. So we actually don't want to do that. That right there is N. Okay, PV equals nRT. We are solving for the pressure. So pressure equals nRT over P. Nope. What is that? nRT over V. All right, N is moles, 0.450 moles. Now you might say, hold on, well, there's also moles of this, right? Well, the gas is what's going to be giving it the pressure. So since that's the only gaseous product, that's going to be our moles of gas. Multiply that by R. You didn't forget this, did you? 0.0821 liters times atmosphere over moles times Kelvin. Multiply that by the temperature, 23 degrees Celsius, but of course you're not going to put 23. You need to add that to 273.15, or in this case 273, to give you 296 Kelvin. We divide that by the volume, which is 1.00 liters. And again, if you didn't catch what I was saying before, technically, if you have that little piece of solid strontium chloride in there, you know, that is space that the gas is not able to occupy, meaning it technically has an acting volume that's a little less than that. Let's not worry about that. All right, let's see what we get. 0.450 times 0.0821 times 296 divided by 1 gives us a pressure of 10.9. What's our unit? Well, mole cancels mole, Kelvin cancels Kelvin, liter cancels liter. The pressure unit in there is atmospheres, 10.9 atmospheres. That would be quite a high pressure little container there. All right. Good luck with the rest of your studying. Of course, come to Extra Help if you need it, and wish you all the best.